Hi, my name is Bill Fortney, and welcome back to Probability and Statistics for Engineers. You should be feeling now like you're getting a good foundation, and we're at the point now where you're actually starting to see the statistics and how it's going to help you understand what to expect when you need information for a decision. And that's really going to come alive in this video as we start looking at how to work with the normal distribution. Okay, just setting the background, we always want to remember this. Everything we're about is making a decision. And you're going to see that as we start learning how to see what to expect, that what answer we're looking for is driven by the decision that we're making. And we've seen that everything that we take when we take data is a random variable. That random variable follows a distribution. There is some distribution. We're going to take a sample, and the average and standard deviation will be used to estimate population parameters, and statistics tell us what to expect. Now, the normal distribution specifically is what we're going to work with right now. And we've been introduced to it before. Across the bottom is the value that we're interested in. Up on the curve is the probability the value will happen. You've seen this equation that describes that. We're going to have tables. We don't have to worry about calculating that. We'll be able to do that. And a couple things about the normal. Number one, obviously it is symmetric. And what we're going to find is that the probability is the area under the curve. I have two values, and I'm wondering what the probability is of getting a value in between here and here. So the area under the curve is that probability. Now, the whole area is 100%. What's the probability of something happening? 100%. If I'm interested in the probability of less than value number 1 and greater than value number 2, that's 1 minus the probability of getting the red area, because everything minus the red is what's left over. And since the normal is symmetric, as long as value number 1 and value number 2 are the same distance away from the mean, then the two equal each other. So if I wanted to know the probability of it being less than value number 1, I could take 1 minus the probability of the red area, that's everything, divide it by 2, and that would be this probability. Okay, just showing you some basic functions because we're going to use that kind of math as we start to work with the normal to get some of the probabilities that we're interested in. Okay, now the normal is really special. It's convenient because the probability of getting a value is based upon how many standard deviations the value is away from the average. And that makes it really convenient. So for example, plus or minus 1 standard deviation. So if our value number 1 and value number 2 are 1 below the mean, 1 above the mean, 68.26% of the time, values will fall in there. Wow, that's cool. Now, plus or minus 2 standard deviations. So if I move down 2, move up 2, 95.44% of the values will fall in there. And if I go all the way to plus or minus 3 standard deviations, 99.74% of the values will fall within that. So right now you just stop and think how much we know about what can I expect. Like if I need to know 99.7% sure what's the lowest value I will have, I can go 3 standard deviations and up 3 standard deviations. I'm not going to have much below that or above that. Now, will I have some? I sure will. How much? 0.13. 1 minus 99.74 is 0.26 divided by 2 is 0.13. So if someone's going to jail, is that going to do it for me? No. And we're going to learn some more how to look at those situations. But we already know a lot in terms of where numbers will fall. Now, we commonly go take some data, take them average, and use that value, don't we? Hopefully you're starting to see, wait a minute, 68% of the time I'm going to be within plus or minus 1 standard deviation, but I'm using this one number right here. Whoa, that's not the whole story, is it? I could get all these other numbers. We're going to see more about that, but that's the thought that I want you to start to have, is realizing that just getting an average is not the whole story. not when we're dealing with random variables, which we are every time we take data from the real world. Okay, so let's say we now have our factory, and we know it's normal with a mu of 81, a sigma of 1. We take our sample average is close to that, and we're using it to estimate. Now, look at what that means of what we know, just that one little bit we've learned. What that's telling us is 68% of the time, we're going to be between 80 and 82, one standard deviation, plus or minus. 95.44% of the time, we're going to be 79 to 83. And 99% of the time, we're going to be 78 to 84. Again, if we're not talking about going to jail, if being out 0.13% of the time is okay for whatever decision we're making, bam, we know what we need. If we need a minimum, we got 78. If we need a maximum, we got 84. If we're like, look, we don't care if some fall out, we just need to make sure most of the time that whatever number we use is going to be within, well, then we could use a 79 to 95% of the time. You get the idea. It's the decision that you're making that tells you what number to use, but knowing this is normal distribution is starting to give us a lot of information, and it gets even better. Now, check this out. So the middle is 68.26, but look at this, the yellow areas. If I take 95 minus 68, I get 27 divided by 2. That means 13% of the time I'm going to be between 79 and 80 or 82 and 83. That's a lot of good information. And then let me do the last one, 99 minus 95. That means 2% of the time I'm going to be in those areas right there. And we already know 0.13% of the time I'm going to be on the other side. Okay, again, wow, that is a lot. Now I'm starting to get very specific to know what to expect. Now, you'll learn how to calculate an exact probability. I want to know what's the probability of getting less than this. You'll learn this. But just in general, what we know from the normal, hopefully you're seeing how much we can know about what to expect from our factory or from helicopter wear that we're measuring or heat coming off, whatever it is, we're going to be able to really start to understand what we can expect. So let's put this in practice. So here's our factory. You see the distribution, average of 81, standard deviation of 1. There's our percentages. And let's say we produce 10,000 bolts a month. Now, I did a little research, and that's not a lot for bolt manufacturers. They produce a lot of bolts. But look what happens. So what does that mean? How many we are going to have in this green area? The math's pretty easy with 10,000. We're going to have 6,826. How about the yellow? We're going to have 1,359, either between 79 and 80 or 82 and 83. And then our red area, we're going to have 215 parts down here between 78 and 79. Now, how many are we going to have on the outside below 78? We're going to have 13 parts. You remember what I said? If we're talking going to the jail, the plus or minus 3 standard deviation doesn't do it. The probability of it being out there is small, but it's not zero. And when you're talking large numbers like 10,000 bolts, it's a lot. So you see, this is the picture of what is really happening. If this was our factory, we would have this many parts in all these areas. Now, stop and think about this for a second. We use an average like it's the number. We need to know, like we're doing something on the wind tunnel and we need to measure lift or drag or whatever it is. We go out to it, we measure some numbers, we take an average. Now we go use that number in a calculation like it's the number. But stop and think for a second. Here's the average right here. How often do we actually hit 81? So here's what I did. I was curious. So I said, okay, let me say, okay, I usually use the average. Let me back off that average just a little bit, a 0.1, because that's the smallest I was able to do with the Z table. I couldn't back off any closer. So 80.9 to 81.1, right in there. What is that probability? You'll learn how to do that in the next video. It's actually 8%, so that's 800 parts. Whoa, wait a minute. What you're telling me is that number that I've always treated as the number we're only going to have 800 parts that actually are at that average this month. That leaves 9,200 parts that aren't at the average. Okay, again, I just want to plant that seed that the way we have typically thought of average and used average as the number isn't right. Well, what number do I use? It depends upon what decision you're trying to make. If if you just need a number that represents the most likely number you're going to get, and if you vary off some from that, it's not going to matter, average is probably your bet. But if you are doing something where if it's smaller, it matters, you may need to use one of these numbers. Which one? It depends upon how certain and your decision is going to drive that. And you'll learn the tools to calculate the probability of whatever it is you need. Okay. The other thing that I want to point out on that is if I'm your boss and you tell me our factory is operating at 81 and you don't give me an idea of the amount of variation, you're misleading me because that's not true. Our factory is not producing at 81. It's producing at 81 with a standard deviation of 1 and a normal distribution, following a normal distribution. So we're going to routinely get parts all the way down here and we're going to get some below 78. So do you see that? Without you telling me about the variation, you're not giving me the full picture. That's why when you report a number, you always want to report the variability with it if it's something that people need to know and that matters. Okay, now let's see what that actually looks like if it was your factory. So if you will, take the normal distribution, turn it on its side. We still have these same areas. We still have the same range. There's the average going up, going down, plus or minus 1, 2, 3 standard deviations. Here's our percentages. And now, instead of 10,000, because 10,000 is too many to see, 1,000 is really too many. Let's say our factory makes 1,000. And I'm going to plot them across the page right here. So first, a couple of questions. How many am I going to have between 80 and 82? Think about that for a second. How many points would I have in between this area right here spread across the page if I plotted 1,000? Think about that. Okay, hopefully you thought of 1,000 times 0.68 or 341. And how are those 341 going to be distributed in here? They're random. They're going to be just bouncing around in there. Some will be close, some will be they're just randomly spread around in there. Okay, so how many would I have between 82 and 83 or 80 and 79? Think about that for a second. Look at our percentages. Hopefully, you saw 1,000 times the 13.58%, 135. How are those going to be spread around? Same way. They're just randomly going to be spread in there. Because remember, the Galton board, you can't tell where any one is, but you know a pattern. What's the pattern? Well, we know how many are going to be in here. Where's this one and that one? They're just going to be randomly spread. Okay, how many are going to be between 83 and 84? I think you get the picture. We're going to have 21. How many are going to be greater or less? 1.3. Okay? But again, do you see how these percentages and understanding the average and the standard deviation start to give you a picture? If you know it's normal, average, and standard deviation, you have an idea of what it looks like. You could sketch it out. So here's the actual graph. Like I said, 1,000 is a bunch of points. But let's check some of these. So we're supposed to have 21 between 79 and 70 and 78. Let's check it out. 1, 2, 3, 4, 5, 6, 7. I think there's another one. 8, 9, 10, 11, 12, 13, 14, maybe 15, 16, 17, 18, 19, 20. Whoa, lo and behold, look at that. If I was to count these up here, you would see just about the same thing. How about lower than 78 or more than 84? A little over 1. Bam, we got 1 right there. We got 1, 2 right there. Do you see that? This is true normal data with that average and that standard deviation. That's what it looks like. Now, this next one, I'm going to do it with fewer points just so you can get a look at what it looks like. Because remember what I said, what are the points going to look like in this range right here? How many of these are we going to have? We're going to have about 68. I am not going to go count them. But notice they're just bouncing around however. Sometimes they go up, down. Sometimes you'll see a pattern. Boop, boop, boop. Sometimes boop, boop. Looks like they're bouncing. They're just randomly bouncing around in there, okay? And now you notice, how many should we have out? Well, none. It's not only 100 parts. Whoa, we got one out. There's a problem. No, there's not. Remember, you can get a point anywhere along here. That Galton board, most are going to fall in the middle. But if the conditions are just right, and you only have 4 parts, one of those 4 could have been the conditions that threw it out on the outside. Again, that's why I keep saying the mentality that the average gives you the whole picture is wrong. You have to understand the distribution and how much standard deviation that you have to really get a good idea of what can I expect on this thing to make the decision that I want to make. Okay, so note the randomness within the ranges I showed you, and then I keep highlighting that idea you're not always going to get the average. Okay, so this is what that picture is going to look like. I already mentioned to you, you're misleading if you don't tell someone the amount of variation along with the average, and everything is always driven by the decision. All right, one last thing. The amount of variability, the standard deviation in our process makes a huge difference in what we can expect. That's why if you don't tell me, if you don't consider variation, the picture of what to expect is incomplete. And I want to show this to you. You remember when we were talking about average, to explain those, I showed you these graphs with 3 different standard deviations. And I graphed them out here for you like this. Now let's join this knowledge with our knowledge of distributions. So here is the standard deviation of 1. So you see our range here, our percentages, and I think there's 20 points here, and I plotted them. Same graph that we had before, just I did a different set of random numbers, so it's not going to look exactly the same. You could multiply these by 20 and count, and you're going to get roughly in that range. Now look at a standard deviation of 2. The spread of our normal curve has doubled. The percentages are the same, but the spread has doubled. And look, we now go from 75 to 87 instead of 78 to 84. And I'm going to put the graphs next to each other so that you can see. So look at what's happened to what we can expect. The range of what we can expect is way wider. So in one sense, you can say it's harder for me to know what to expect because I got a way wider range to pick from. If we're talking about, okay, what number would I use to capture 99%? I could use 84 if it's my largest. Over here, if I used 84, I'm still right in here where there's a bunch of parts that are going to be out there. 99% of these are still within, this is going between 1 and 2 standard deviations right in there. So you see, what can I expect has gotten way harder because the range has gone up. Let's run that the other way. Now remember we had the 0.5. And now look at my range on the 0.5. I go from 78 to 84. Now I'm going to 79.5. And again, I'm going to plot that. You can compare these two. Now it's just the opposite. This guy, my 99% right here, whoa, that's still right in the middle of this guy. There's still a whole bunch more points. And now I'm going to throw these all on the same graph just so that you can see. Variation is not our friend when it comes to knowing what to expect. A lot of what we do with our designs impact variation. Impact how much variation they're going to be when the part is made, which makes it that much harder to know what's expected. When we design experiments, if we don't control things well, there's variation. That variation makes it harder to know what to expect. So I said I'm trying to help you develop an intuitive feel for these things. When you look and one has a larger standard deviation than the other, immediately what should be going through your head is it's going to be harder to know what to expect from that one. It's going to have a wider range. Just like you can see here, going from 0.5 to 1 up to 2, the range of what we could expect drastically increases. And that's the reality. That's why I said before that we have to couple all our knowledge of average and standard deviation with the distribution. Then it's going to be powerful to help us understand what we can expect. Okay, so one thing I wanted to point out was the impact of standard deviation. I've done that. The other was how it is reasonable to get any number in that range. I keep saying that we cling on to this average, but it's not just the average. Because you look over here, I use the average, and hey, 68% of the time, I'm going to be pretty close to that average. Over here, 68% of the time, I'm going to be pretty far away from that average. So, dependent upon the standard deviation, we could get way far away from that average, and any number in this range, all the way from plus or minus 3 standard deviations, and even a little past, in reality, any of those numbers could come up. So you have to consider that when you're making your decision. The average is not the whole story when you're making your decision and when you're reporting your results. Okay, so hopefully you see now the average and standard deviation with the distribution tells us a lot about what we can expect. And in the next video, you'll learn how to actually calculate the specific probabilities that you need and answer those original questions when we were asking about the bolts or about heat coming off or whatever it is, and you'll be able to calculate exact probabilities.